Alright, chemistry, we're on to a 2-lesson unit called Thermodynamics. Our first lesson is on Gibbs free energy. So what is thermodynamics? Thermodynamics is the study of energy into or out of a physical system or chemical process. Physical and chemical processes want to move to lower energy. Take the following chemical reaction and its reverse. 2H2 plus O2 gives you 2H2O, or the reverse is 2H2O produces 2H2 plus O2. Which of these reactions will happen naturally? The one that will take the reaction to the lowest energy state. But which one is that, and what kind of energy? We have already dealt with energy in the form of enthalpy, delta H, and that's heat energy, in the unit on thermochemistry, so that was back near the beginning of the course. Enthalpy is the transfer of thermal heat energy into or out of a chemical reaction at constant pressure. So there we see a combustion reaction of methane, and it releases energy. That's an exothermic reaction, releases negative 890 kilojoules per mole. An exothermic reaction occurs when heat comes out of a reaction and has a negative sign. So that's like money out of your bank account. So this is all review of Unit 5. An endothermic reaction occurs when heat goes into a reaction and has a positive sign. That's money into your bank account. There are two basic rules of physics that describe how chemistry works. Negative attracts positive and negative repels negative. Those are Coulombic forces. Chemical processes naturally move from higher to lower energy. Some reactions are endothermic, which means that the reaction takes in energy and ends up at a higher energy level than it started. So far, this is the only kind of energy we talked about, is enthalpy. That's what we talked about back in the thermochemistry unit. That's delta H. If chemical systems must move from higher to lower energy, then there must be another kind of energy we're talking about. In other words, if chemical systems have to move from higher to lower energy, it would be and the only kind of energy was enthalpy, delta H, it would be impossible to go from to have an endothermic reaction, to go from lower energy in the reactants up to higher energy in the products. But that does sometimes happen. So that must not be the only kind of energy if that process can happen. This lesson deals with a new kind of energy called Gibbs free energy. By computing Gibbs free energy, also just called free energy, of the reaction, we can determine which way the reaction will naturally run. Free energy is abbreviated G. 1. If the change in free energy is negative delta G, is less than 0, then the reaction will naturally flow in the forward direction. In other words, it's releasing free energy, and that means that energy is going from a higher level to a lower level if delta G is negative. If the change in free energy is positive, that means it's taking in free energy, then the reaction will naturally flow in the reverse direction. 3. If the free energy equals 0, delta G equals 0, then the reaction is at equilibrium and it won't flow in either direction. In this unit, you will learn to compute free energy from standard free energy, which is symbolized by G with the little circle above it, and the reaction quotient studied in the equilibrium unit. By the end of this unit, you will be able to determine which way a reaction will run naturally based on external variables such as temperature and the reaction quotient. So what is thermodynamics? Thermodynamics is the study of free energy into or out of a physical or chemical process. The process can be a chemical reaction such as 2H2 plus O2 produces 2 water molecules, or it could be a physical reaction such as the melting of ice into liquid water. So that would be H2O solid into H2O liquid. In this unit, we will use 3 laws of thermodynamics. The first law of thermodynamics states that energy is neither created nor destroyed. The second law of thermodynamics, the entropy, to be defined later, of the universe increases in a spontaneous process. And the third law is that the entropy of a perfectly crystalline substance at 0 Kelvin, that's the lowest possible temperature in the universe, the entropy is equal to 0, and entropy is symbolized by the letter S. So a spontaneous process is one that happens naturally with no outside influence. So when Dino drops his pencil, it is a spontaneous process because the pencil falls naturally. When Dino picks up his pencil, it is a non-spontaneous process because it requires energy to take place. The word naturally was used earlier. It meant spontaneously. A spontaneous process is one that happens naturally with no outside influence. So a car will spontaneously rust, but to restore a rusty car would be a non-spontaneous process, and it would require an input of energy. Entropy is in disorder in the universe for any spontaneous process. So a broken wine glass has greater entropy disorder than a wine glass that is not broken. The symbol for entropy is S. The units of measure for entropy are joules per degree Kelvin, or per Kelvin, joules per Kelvin. So entropy equals disorder, remember that. Increasing entropy means you're increasing the disorder of the system. The units joules per Kelvin can be understood with an example. If heat measured in joules is released into a hot room, that is with a high temperature Kelvin, it hardly changes the motion of the molecules. This means that there is a small change in entropy when the ratio of joules to Kelvin is low. So the molecules are already moving quickly. Some more heat is only going to make them move a little bit more quickly, and that's going to increase the entropy by a very small amount. So you would not feel any heat in an already hot room. The small increase in the speed of the molecules is a small delta S, that is change in entropy. Example, you're sitting in a room that is 310 Kelvin, and that's hot, about 100 degrees Fahrenheit. The units, joules per Kelvin, can be understood with an example. If heat measured in joules is released into a cold room, low temperature, it speeds up the slow-moving molecules greatly. In other words, their speed increases greatly from what it was. This means that there is a large change in entropy when the ratio of joules to Kelvin is high. You would feel the heat in a cold room. The large increase in the speed of the molecules is a large delta S. Okay, the units joules per Kelvin can be understood with this example. Example 1. 50 joules of heat is released into a 400 Kelvin room. That's pretty hot. What is the change in entropy? So it's 50 joules over 400 Kelvin is 0.125 joules per Kelvin. Example 2. 50 joules of heat are released into a 200 Kelvin room. That's cold. What is the change in entropy? It's 50 over 200, so it's 0.25 joules per Kelvin. So twice as much of an entropy change because the relationship of the heat to the temperature is much greater. The heat has a greater effect on the entropy of a cold room, and you would feel the change in entropy more in the cold room. Entropy is an increase in disorder for any spontaneous process. Dissolving an ionic compound such as potassium bromide is a process that is both spontaneous and increases entropy because the ions are in a greater state of disorder. In chemistry, entropy is the number of possible ways that atoms or molecules can be arranged. The more possible arrangements means more disorder and therefore more entropy. So ice, the H2O molecules are arranged in a specific order. This is low entropy. Water, in liquid, the H2O molecules have more freedom to move around. This is greater entropy than ice. And in vapor, the H2O molecules are completely free to move around. This is the greatest entropy. A spontaneous process must be irreversible and increase the entropy of the universe. So Rule 1 means that the reaction cannot be spontaneous in both directions. If it is spontaneous, that is, happens naturally in one direction, it cannot happen spontaneously in the other. A pencil cannot spontaneously fall from your hand to the ground and also spontaneously fly from the ground back up to your hand. And Rule 2 means that you can decrease entropy, disorder in a system, but the entropy of the universe must increase. When life on Earth formed, this was a great increase in order, that is, decrease in entropy. However, the entropy of the entire universe had to increase by a greater amount than the decrease in entropy on the Earth. So example, Mr. Peabody's class is behaving badly. The class has high entropy disorder. He asked the principal to send other teachers to help manage the class. So there's the other teachers, and there they go. They're going to go over to help him manage that class. So Mr. Peabody's class is the system, and the rest of Hoover is the surroundings. Together, Mr. Peabody's class and the rest of Hoover are the universe. So you remember those terms, system, surroundings, and universe. Mr. Peabody's class is now more orderly. The entropy has decreased. However, with all of the other classes unattended by teachers, the overall entropy of Hoover and Mr. Peabody's class, the universe, has increased. This means that we can decrease the entropy of a specific system, Mr. Peabody's class, but the entropy of the universe must increase. Factors which affect standard entropy are the states of matter. Gases have greater entropy than liquids, and liquids have greater entropy than solids. Molar mass. Entropy increases with as molar mass increases. Allotropes. Different allotropes have different entropies. Allotropes are two different forms of the same element in structures. For example, graphite and diamond are both allotropes of pure carbon. Dissociation. When an ionic compound dissolves in water, it will have greater entropy than the solid. So NaCl dissolving into sodium ions and chloride ions moves to greater entropy. And molecular complexity. An increase in the complexity of a molecule increases entropy. Molecules can have three kinds of motion. Translational motion, this is the motion of a molecule from one place to another. So when this molecule moves from point A over to point B, that's a translational motion. Vibrational motion, this is the motion of the atoms within the molecule. So the molecule can wiggle, it's wiggling. And rotational motion, this is the motion of a molecule spinning in place. So there you see a molecule just continuing to spin around and around. And that's rotational motion. More complex molecules can have more of each of these motions, so they have greater entropy. There are two principles that determine the direction of a chemical or physical process. One is a process tends to move from higher to lower energy. And two, a process increases entropy of the universe. So sad as it is to say, the universe wants to increase its disorder. It wants to naturally move from more order to less order, to greater entropy. So the ice cube example is one I really want you to nail down and understand, because it really explains this relationship and this concept really well in an example that's simple for you to understand. Ice cubes melting to water, or water freezing into ice. So when an ice cube melts to liquid water, heat enters the ice cube. That's positive delta H, and the ice moves to higher energy. Now that's not natural. That's an endothermic reaction. It's not natural for heat to want to go into a reaction and raise the product, raise the end result up to a higher energy. So that's not natural. So this violates Rule 1, that a process tends to move from higher to lower energy, because in this case, the ice cube is going from lower to higher energy. Now, when ice melting also increases the entropy, the disorder of the ice cube. In other words, the molecules of water become more disorderly. And that obeys rule 2. So one of the rules is violated and one of them is obeyed. So just stop for a moment and think about that. Heat going in is not natural, and that violates rule 1 of going from higher to lower energy. However, the ice cube becomes more disorderly, that increases entropy. That obeys rule 2, that the entropy wants to increase. Okay, now let's go in the other direction. When water freezes into ice, heat leaves the water to bring it to a lower energy state. So think about that. The water has more energy, and then heat comes out of it, and that freezes the water into ice. So that's natural. That obeys rule 1. So this obeys rule 1. However, when water freezing to ice creates lower entropy in the water molecules as they become fixed in an orderly pattern. We've seen water in its form of ice. It makes these nice hexagons. So that violates rule 2, that the process is going to become more disorderly. So ice melting to water obeys one of the rules and violates one of the rules, and water freezing into ice obeys one of the rules and violates one of the rules. So something's got to be the tiebreaker to determine which of those two things is going to dominate. Is rule 1 going to dominate or rule 2 going to dominate? So if you use your common sense and think about what determines whether water freezes to ice or ice melts to water, you already know the answer to that. So the preceding 2 slides show the conflict between the 2 rules. A process tends to move from higher to lower energy, but a process also wants to increase the entropy of the universe. We know that the primary factor that determines whether water freezes to ice or ice melts to water is temperature. So the combination of enthalpy, delta H, entropy S, and temperature T leads to a new definition of energy called Gibbs free energy, which is symbolized by capital G. The formula for Gibbs free energy, also called free energy, is delta G, that's change in free energy, equals delta H minus temperature delta S. So enthalpy minus the temperature times the change in entropy. So there you see, now we're not just dealing with the only type of energy that we've dealt with up until now, which is enthalpy, heat energy. We now have another factor involved, and that's the entropy. And based on the temperature, one of those two will dominate, either going to lower heat energy or going to higher entropy. The temperature will kind of be the tiebreaker and determine which one dominates the reaction. So the units of measure for delta G is joules or kilojoules because it's a form of energy. And joules or kilojoules is the unit of measure for any form of energy. So when we say chemical systems want to move from lower energy, we don't mean just enthalpy anymore, delta H. We mean free energy, delta G, which is a battle between entropy and enthalpy. So free energy is determined by entropy and enthalpy. Entropy means more disorder and higher energy. Enthalpy means less disorder and lower energy. Temperature determines which of these two factors dominates the battle. So there's enthalpy, there's entropy, and temperature is in between them to determine which one is going to dominate a particular reaction. So the key point about change in free energy delta G less than 0, the forward reaction is spontaneous, moving from left to right, the way we normally would think of a chemical reaction as moving, and the reverse reaction is non-spontaneous. So think about delta G less than 0. What does that mean? It means negative delta G. It means delta G is negative. That means the energy is going out of it, and that means that the free energy is being lowered. So when we say systems want to go from higher to lower energy, we're not talking about enthalpy necessarily, we're talking about free energy. That's the real energy that we're dealing with here. Delta G is greater than 0 is positive. That means free energy is going into the system. That would make the forward reaction non-spontaneous. It won't happen naturally. So key point, delta G is negative. The reaction is spontaneous in the forward direction from left to right. Delta G is positive. The reaction is spontaneous in the reverse direction from right to left. Okay, so the process tends to move from higher to lower energy. and the process increases the entropy of the universe. Those are the two things that are natural. So let's look at each of these four possible combinations. We have a little matrix here. So if delta S is greater than 0, that's more disorder, that's natural. That's what the universe wants to do. And if the reaction is exothermic, it gives off heat energy, that's also natural. That's what the universe wants to do. So that reaction is definitely going to go forward if it has both of those characteristics. So delta G is going to be less than 0. Your free energy is going to decrease. That means the reaction is spontaneous from left to right in the forward direction. So the situation in red shows entropy increasing and heat energy enthalpy decreasing. This obeys both rules, so this is a spontaneous reaction. Now let's look at the reaction down here. Delta G is greater than 0. Why? Because you've got your entropy, delta S, decreasing. That's less disorder. That's unnatural. And you have your enthalpy increasing. That is, heat is going into the reaction. That's also unnatural. So that is not going to be a natural reaction. That is not something that's going to proceed in the forward direction from left to right. So the situation in red shows entropy decreasing and heat energy increasing. This violates both rules, so this is a non-spontaneous reaction. Okay, next situation right here. We have delta S is less than 0. It's decreasing. That means the entropy is decreasing, so the reaction's becoming, or the situation is becoming less disorderly. And over on the left, you see delta H is less than 0, so it's exothermic. So think about the ice cube. Is that water freezing to ice, or is that ice melting into water? Less disorder and exothermic. That would be water freezing into ice. Okay, it's becoming less disorderly, so ice is very structured, and it's exothermic. Heat is coming out of the water to turn it into ice. So when does that happen? When does that happen spontaneously? That happens at low temperature. Low temperature, delta G is less than 0. That means free energy is being lowered, so that happens spontaneously. At high temperature, water does not freeze to ice. We all know that. So that would be delta G greater than 0. That is non-spontaneous. So the situation in red shows entropy decreasing, and this violates Rule 2, and heat energy decreasing. This obeys Rule 1. So this is the situation when water freezes to ice. So this will be spontaneous when the temperature is low. And then the last situation. Now we have entropy is increasing. That's more disorder. That's what nature wants. But we have heat going into the reaction. That's not what nature wants. Heat doesn't naturally go into a reaction. So what is that? That is ice melting into water, liquid water. It becomes more disorderly, and you have to put heat in to make ice melt into liquid water. So when does that happen naturally, spontaneously? That is, when is delta G less than 0? It's when you have a high temperature. High temperature will make ice melt into liquid water. It will not happen at low temperature. That's delta G greater than 0, so that won't happen spontaneously. So the situation in red shows entropy increasing. This obeys Rule 2, and heat energy increasing. This violates Rule 1. This is the situation with ice melting to liquid water, so this will be spontaneous, delta G less than 0 when the temperature is high. Alright, and that takes care of this introductory lesson on thermodynamics.